Levitating Balloons by Group 5B. In this lab, we will be determining the charge of two balloons using Coulomb's law by finding the acceleration of the balloons repelling using tracker software. This will allow us to find the force. We can then set the force equation equal to Coulomb's law to solve for the two charges of the balloons, assuming that the two charges are the same. The results are shown below. Our system schema shows an electric interaction between the two balloons. Our force diagram shows the two balloons repelling away from each other, and this is because it is known that like charges repel. Our energy pie charts show that at time 0, the charges are not interacting and all of the energy in the system is potential. At time equals 1, charges are brought close together and potential energy and kinetic energy are split 50-50. At time equals 2, the charges are fully repelling and the energy in the system is kinetic.
One main physics idea that we explored in our lab is Coulomb's law related to electric force. The law states that the force is equal to the Kc constant times the charge of the first balloon times the charge of the second balloon over r squared. R squared is the distance between the charges. It's important to note that the magnitude of the force is dependent on the magnitude of the charges of the balloons and the distance between them. Charges of the same sign repel and charges of the opposite signs attract. Another main physics idea that can be explored with our lab is Lennard-Jones potential. Lennard-Jones potential examines the interaction between a neutral pair of molecules or particles. In our lab, however, we assume that the balloons are of the same charge, so they will be repelling each other. And repulsive forces occur when the electron clouds of the molecules are overlapping and they cannot come any closer in distance without them repelling each other. As shown on the graph, when these repulsive forces do occur, the potential energy increases greatly. For our lab, we made some assumptions. We had assumed that balloon 1 and balloon 2 have the same charge and that they are also of the same mass and are inflated to the same size. And since we made those assumptions about the balloons and their charges and size, we were able to set F equals mass times acceleration equal to Coulomb's law. For our experimental design, we collected two balloons of the same mass and inflated them to the same size and then recorded their mass again to make sure that they were equivalent. For each balloon, we tied a string to the end so we'd have something to hang on to when we performed the lab. We taped a meter stick to the wall to provide a basis for our measurements when using tracker, and we charged both the balloons using a scarf, assuming they were both at the same charge. We would move the balloons towards each other and repeated this 3 times while recording a video to use for tracker software later. Using tracker, we analyzed the interaction to determine acceleration and r squared values. We used acceleration to determine the force in the system and Coulomb's law to determine the charge of the balloons.
To begin our experiment, we inflated both the balloons so that they were the same mass of 2.93 grams. We then took a video of them repelling and put it into tracker, where we were able to find the acceleration of the repulsion as 0.28326 meters per second squared. We also found that the distance between the two balloons was 0.358 meters. We already had Coulomb's constant. We used this data to do the calculations. We set the two force equations equal to each other, and we assumed that the balloons had the same charge, and we were able to find that this charge of the balloon would probably be around 3.44 times 10 to the negative 6 coulombs, and this could be either positive or negative, but they would have to be the same. So our results gave us a charge for the balloons of 3.44 microcoulombs. We also calculated the number of electrons that was transferred to the balloon when we were charging it by dividing 3.44 microcoulombs by the charge of an electron, and we found that 2.15 times 10 to the 13th electrons were transferred during the charging of the balloons. Our model was not very accurate since the data was collected with tracker, which is not the most precise instrument. We did do 3 trials, however, and we used the average acceleration and distance data from each to improve the accuracy. However, there were more limitations of our model and some human errors. When we were holding the balloons so that they could repel, we did touch the balloons, and that could have changed the charge of them, as some of it could have been transferred to our hands. We also could have had different charges initially, since it's kind of hard to measure how much you're charging the balloon with. Trials 2 and 3 could have also had increased charges than trial 1 did, since we recharged between trials. As far as our data goes, velocity and acceleration were only calculated in the x direction, and we decided that the y and z directions were negligible. If we had taken those two into account and if we had measured angles, we would have gotten a more accurate number for our charge. Also, we only tracked the acceleration of one of the balloons. We assumed that the other balloon was fixed, but it was hard to keep it in one position. So this could lead to an underestimate of the force that we calculated.